is a new age of physics and the understanding of our universe. We've never before seen these unprecedented energies that the collisions will be at the Large Hadron Collider. Whatever is out there, we're bound to see it and we're bound to discover more and essentially rewrite the textbooks.
These kind of detectors and experiments come about once in a generation, and it is a great privilege to have been part of this from the start.
This looks like a lovely crystal, but it's actually really heavy. I can only just lift it. This is part of the electromagnetic calorimeter, so particles get detected here. They produce light in the crystal that is then detected by this piece of electronics here.
One of the possible things that we'll see at the LHC are signs of a new particle called the Higgs particle. Now, if this exists, it could explain why some other particles are heavy and some of them are light. This detector in particular will really give us a handle on whether this Higgs particle exists or not.
I'll be very, very surprised if something isn't found soon.
Thank you, Mr. Ellis.
This is a very unusual place to be. Most of the visitors who come to look at Atlas don't actually get allowed to come right in the heart of the experiment, which is where we are now. We're just underneath where the beams of protons from the Large Hadron Collider are going to collide. Atlas is the largest of the 4 experiments that are being assembled around the Large Hadron Collider. What we're really hoping is that Atlas is going to give us some clue into also the mysteries of astronomy. We know if we look out at the cosmos, there's a certain amount of visible light from stars and so on, but the way they're moving, astronomers and cosmologists know that there's actually more matter out there. There's some dark matter out there which has so far not been observed, something really new. We're hoping that in Atlas we will actually be able to create particles of dark matter.
On the cosmological scale, we're reproducing here by colliding 2 protons at these energies, events which happened right at, we believe, at the Big Bang.
The sheer amount of power we need means that we start with the very highest voltage, 400 kilovolts from the French network here. If we're going to find new particles, we have to put a lot of energy in to create a small amount of mass. And the sheer amount of the hundreds of megawatts that we draw from here to produce these very smallest particles is very impressive. Here we look after the operation of the main accelerators, the whole of the accelerator chain, all beam operations, and the general infrastructure of the site as well.
The LHC is a voyage into the unknown. It's tremendously exciting because we really don't know what we're going to see. The green curves you can see here belong to the magnet inside the LHCb experiment. What happens when we have a beam collision is we create lots and lots of fundamental particles, very energetic ones. They rush out in all directions, and the job of this magnet is to deflect them, and that allows us to work out how fast these particles are going. We've never looked so deeply into the heart of matter before.
Finding extra dimensions would be much more exciting than finding a ball-bearing Higgs boson, possibly even more exciting than finding dark matter. This would be telling us something really basic about the way in which the universe is constructed, telling us something which you would never have guessed, right? It's something completely unexpected if it's true.
My group are involved in the ALICE detector, and what's unique about ALICE is that as well as colliding protons together, we take lead atoms, we strip off all the electrons, put them in the LHC, collide them to the maximum energy. We create an incredibly intense fireball. Now there's nothing to be afraid about because this fireball is much, much smaller than the size of an atom, but it's incredibly hot and incredibly dense. In fact, it's about 1,000,000 times hotter than the centre of the sun. And it's so dense, it's a bit like taking one of the great pyramids of Egypt and crushing them to the size of the pinhead.
This is really the biggest and most complex scientific project ever undertaken. The whole 27-kilometer circumference is aligned to better than a tenth of a millimeter. But the way that we cool the machine down is very unusual. We are using superfluid helium, which is a very, very odd liquid. It's a quantum liquid. For instance, if you put it in a beaker on your table, then the liquid would just crawl out of the beaker. Obviously, it's a terrific engineering challenge to make this completely fail-safe. And this is an essential feature of the LHC. I think it's the first machine in the world that's got the capability of destroying itself.
So this is ScotGrid. This is where we're about to receive all the data from the LHC. You can see this is a typical regional data center. This is where we hope we'll see the first data which might tell us all about the Higgs. In order to handle the large amounts of data which come from the LHC, we decided to build a successor to the World Wide Web, and we called it the Grid, which incorporates sites around the world, including Glasgow, and this enables us to meet the analysis challenge.
The detector for a Large Hadron Collider is constructed a little bit like a set of Russian dolls. We in Glasgow have been working on the vertex detection, the close-in silicon tracking. We're in the innermost layer of this. You can see how it's designed as a mosaic of tiles. Each of these tiles can detect and accurately measure the position of particles going through it, and this is done 40 million times a second. There's a lot of intricate work to do. Across each join there are something like 500 little gold wire joints.
Now, if we want to make a top quark at the Large Hadron Collider, when we start up this project at Atlas, when the first collisions occur, then our role in Birmingham in contributing to the detector will become vital. Because one of our key roles is to try to decide which of the collisions to record onto computer and process and try to analyze.
I'm working on minimum bias trigger and trigger for first physics, and actually looking at how the trigger biases the events that we collect.
I'm looking at the phi meson, which is a particle that will be produced in the collisions, and it's made of a strange quark and an anti-strange quark. And these are really interesting because things that have strange quarks in could be a signature of a quark-gluon plasma.
Everybody from all over the world is going to come to Europe, and that's going to be the center of all the activity, and I'm right in it.
People have a lot of stereotypes about people doing physics, that they should be all male and that they should be wearing cardigans with patches on and glasses with tape around the middle. And no, we're not like that at all. So. Well, some are, I suppose. But.
For me, as a theoretical physicist from Cambridge, I've got to look at the results after they've come out and actually after they've been published. Theoretical physicists think in a peculiar way. We have on the coffee tables, we have glass and pens there, and there are blackboards everywhere. It's very annoying not to be able to write something down if you need to. I'm sure I dream about the mathematics in my sleep, and I've solved problems in my sleep. CERN is a hot pot of all the best brains around that are interested in particle physics. It's the temple of physics, and all the top acolytes go there.
Time can behave like another direction in space under extreme conditions.
The UK, through the Science and Technology Facilities Council, is one of the biggest contributors to CERN and hence to the construction of the LHC. And I'm very glad to say that the British government has been very supportive of CERN and the effort to build the LHC all through the times when it seemed like it was going to be impossible to bring the project to a successful completion.
The two big experiments, CMS and Atlas, both have significant UK involvement, as well as the other two more specialised experiments, ALICE and LHCb. So we're really everywhere.
By the UK being involved in this exciting project, it actually opens up a lot of opportunity for young, bright physicists and engineers to really be involved in cutting-edge technology and cutting-edge research.
I think they will achieve something they can be proud of. I think as a DG, I think I should be not so much proud and thankful to all these guys which have been working so hard. because without all this motivation, all this dedication, nothing could have happened. And now we are ready to see the benefits. The LHC is a compulsory tool. Without the LHC being built, we will know that a big part of the knowledge is missing and we'll have no way to discover it.